Thank you, Professor Baldwin, for your mini course, and unfortunately, this is the last day of your mini course.
Yes, yes. Well, thank you again for the invitation, and I've had very many interesting conversations here. Wait, am I not? Are you hearing me? Okay, good. So, what? There's something playing. Oh, that got it. Okay, fine. All right, very good. So there's a couple of, this is being worn because it was my lecture in Chicago for South Bend this morning. This is the official T-shirt of the forking festivals from the early 80s, which were when I managed to get my first book written by having a week every summer and two editions from mostly 100 miles around, came and kibitzed, said, no, that doesn't work, and then I'd rewrite it and we'd look at it again next summer, and also move a little bit further through understanding Shalom. And secondly, we've this is new material. I mean, not we got through what I had prepared, so we're going to look at something different, which is more mathematical in the sense. I mean, we do deeper mathematics, discuss deeper mathematics, but it kind of raises the question. I'm going to be using more sophisticated logics, and how much is that necessary, and to what extent does it fit into Rodrigo's program? So I'm going to start with a description of Zilber's program, and then we will be looking at exactly how that works out, or not exactly. I mean, I'm not going to go through detailed proofs, but I'm trying to give some indication of how these arguments go, what they're about to begin with, and how a slight difference in the hypothesis makes a very big difference in how hard the proof is, and in some ways what methods are available. So this is Zilber's talk from the Logic Colloquium in Paris in 2000. And the question marks are, I'll get them fixed, but this morning I didn't have time to fix them. I messed up something in my bib file, and one of the graduate students says, oh, you can use this program and it'll fix it. And fixing was, it changed the names of all the files. And so I pick up something that I've given a name to and it isn't there. So the initial hope of this author, I think that is probably his ICM speech, is that any uncountably categorical structure comes from a classical class, that comes from a classical context, was based on a belief that logic, the hope is that any uncountably categorical structure comes from a classical context, which seems a bit strange, because we can certainly create crazy things. I mean, Zilber, the Reshevsky constructions are not coming from a classical context. Now, Paolini and I built back into them and got some Steiner systems as examples, but the original thing was not. Could not, well, I think it's more the other way. He wants to say, if you have something that is canonical, then you want to give the description. So instead of comes from, well, oh yeah, there's a missing that, which is, I mean, there's no reason that Zilber should get his English exactly right. Was based on the belief that logically perfect structures could not be overlooked in the natural progression of mathematics. Allowing some philosophical license here, this was also a belief in a strong logical predetermination of basic mathematical structures. As a matter of fact, it turned out to be true in many cases. Another situation where this principle works is in the context of orbital structures. So you kind of get a motto that a canonical structure should have an informative description, and that is an axiomatization that is more than a mere description. Somehow well, I guess it's what we're talking about. That it's going to encompass. It's going to exemplify the concept. Oh, yeah. Okay. Did I go past? No. Okay. The geometric value of the project is perhaps in the fact that the formulation of the categorical theory of the universal cover of a variety V, and we'll say a little more about what that means, is essentially a formulation of a complete formal invariant of X. So that is that we're, I think I say this on the next page, that discrete, so by discrete logic, I mean as opposed to continuous logic, we're doing classical model theory, the structures as given do not have any do not have a topology. There's although it may be definable, but so it definable functions on an algebraic closed field of characteristic of size continuum is actually analytic because the algebraic structure determines something categorically, and so something that you know from the analysis is true, but you don't need to have a second order definition of the continuity or a continuous logic. The structure is determined by the discrete kind of algebraic as opposed to analytic in vague terms. Now what happens here? Do I? And so I didn't manage to get. Actually, I think I've just got these in the. What have I done? I can't. Here. All right. So, what I'm going to say about a full formalization is something that works in some sort of logic. The logic's going to determine. We will definitely specify the vocabulary in advance. This isn't second order logic where you can do anything. And then you have a notion of truth. I mean, just these, and I'm going to insist on having a rules of inference. And then this is what you set up as times of a logic, and then you have a specific axiom for the theories. I mean, this is what we've been saying all week. Just reminding us. So, three interesting logics are L omega omega tau, and L omega 1 omega, and second order. We know what this means. We didn't really need a slide. Now the project contains, Dilber actually started out with this in thinking specifically about complex exponentiation. Can you axiomatize? Here's a classical, so how am I going to get a hold of that? And so that's the, so the first one though, this is an easier case, right? You only have the addition. So now you're talking about the affine space, not including the multiplication. And but the exponential map is still a projection of the of C2 onto C. And this is what he's really after. And now I don't think I've got anything more in the slides, so I'll say quickly that what he finds in this way that we're talking about this for exponentiation is a sentence in L omega 1 omega of Q, which is categorical in all uncountable powers. Whether that sentence is true of the complex numbers has been an open problem for 25 years. And a key to it is the Zilber-Pink conjecture, where Pink is number series, prominent number series. Yes, okay, so the first picture, it isn't really a diagram. I probably had a diagram that didn't get over today. But the first, well, it's a diagram in the categorical sense. Maybe that's what I was thinking of. Is a two-sorted cover of the multiplicative group by the additive group. The full field is studied on the range space, although the kernel is the homomorphism from the additive group. And the second corresponds to complex exponentiation. And the key to getting a hold of this is, I mean, we want to avoid the Gödel phenomenon, right? If it's undecidable, we aren't getting anywhere. There will be many models. But the key to that is to say that the kernel is exactly Z, and so then there are no non-standard models of arithmetic. All right. So I was going to say, try to force us to have a little talk this time. So what does this have to do with what I said before? I mean, I sort of said, but does anybody have any other thoughts? Or, yeah, right. I mean, and there is this question of the actual just the geometry. Yeah, okay. I think, and it's just that we are indeed looking at trying to find these. We have these concepts, and we're trying to get them straight. So, I'm just as a background, the classical categorical theory, categoricity theorems. So, Morley's theorem is, in some sense, the first theorem of modern model theory, is that if a countable first-order theory is categorical in some uncountable cardinal, then it's categorical in all. And that's for first-order logic. Shalal wanted to generalize this to L omega 1 omega, and the best that he could get was assume, I call it the weak continuum hypothesis below aleph omega, and by that I mean two to the aleph n is less than to the aleph n plus 1. Is that what I mean? No, it's less than. Boy. I think it's 2 to the aleph n plus. It's less than 2 to the aleph. I'm sorry, I have not thought about this for a long time. And actually, he doesn't, the fiddling around with, I'm saying there, he doesn't have, but that's because he's trying to get, he uses a more complicated, he gets a somewhat better result with heavier set theory and things that I try to avoid. Now, and the third version is looking at L omega 1 omega for an excellent sentence. And I'm going to say a little bit about let me say right now sort of what excellence is. The key point about excellence is you take a diagram of models like this. So you have elementary embeddings, say, in whatever logic you're after. All of, I've got to have the back. You have 7 of these, right? This would be better if this was a little more parallel. Right? And now, can you get something across the top? Well, no, I'm sorry. I've put them, I think usually one draws the picture this way, and it's this one you have to put in, but it doesn't matter. Right? You've got 7 sides of the cube, 7 edges of the cube. Can you build the 8th? And then you can do that for higher n, right? Just do this in n dimensions. And those amalgamation properties are crucial in this development. An interesting point is that Jacy and the Czechs, well, Lieberman's an American, but he lives in Czechoslovakia, and I'm missing the senior guy, Wyszycki, thank you. They have a paper taking this notion and making it give a notion of independence in categorical terms. And now I'm going to describe abstract elementary classes very quickly, because what we're actually working with is an abstract elementary class, but that's sort of beside the point. But historically, it's not beside the point. So what you have is simply a class of structures and a notion of embedding. Now, these structures are for some particular language, but that's the end of the syntax. We don't have any theory describing the sense. We just have these collection of structures, and then the axioms. Well, it's a refinement of containment. It's a partial order of the set. If you take an increasing chain, then the union is in the class. For each j less than delta, the element is strong in the union, and if AI is it, then it's the union is in the. If you have something above, then the union is actually in it. Now, these three things are equivalent to just saying that it's closed under limits, co-limits. That the class, that co-limits of this relation are preserved. If you take a co-limit of structures under this kind of notion, embedding notion, then it's also in the class, and that's the way the category theorists would think about it. Now there should be one. Let's see the next page. It should have another. There's another crucial axiom. Yes. Now this fourth one just says, it's sort of a Tarski Vought. It says, I have this sitting in here, this is strong in the top, this is strong in the top, then this is strong in the middle. We call that coherence. And finally, and this is the crucial thing, there's a Lowenheim-Skolem number, so that if you have a big model and a small set, then there's a small model containing that set. And now here's another piece of how things fit together. There was a meeting, it was the Czech-Catalan Logic Conference in 2006, I think. And so, yeah, you say Trilafage was there. Eckloff gave a talk about some stuff in module theory, and he had this picture on the board. And I said, oh, well, you're talking about an abstract elementary class. And then we have a couple of papers out of that, and well, Trilafage has done some wonderful stuff. Now, what are abstract elementary classes? And the basic idea was, let's generalize Freire and Janssen, where you have axioms more or less like this, but the embedding relation is fixed as being substructure or subalgebra for Janssen. And well, but here, first order theories with elementary substructure, if you just take for all there exists, this is, what is it exactly? In 51, it's Wash and Tarski, maybe. And then, these are, I was talking about having, no, I wasn't, that was a different talk, sorry. All right, LN sentences, this means we're thinking about the finitary logic with finitely many variables in finite varieties and universal subpoint classes. That's what I meant by Janssen. Models of sentences of L kappa omega were, and models of sentences with different things currently changed. One point I didn't have in this, but it's become very important with the work of Marcos Mazzari, looking at modules. And then two choices are substructure and pure substructure. And he gets many theorems about characterizing the ring where the modules are AECs with various properties. And yeah, okay, I don't think I'll go into the others. Now, Zilber's notion I could put it on this list that I just had, but it comes at it from a different direction. You have, well, first, a combinatorial geometry is simply, well, a closure system is something that closure is a map from subsets to subsets, which is closed under union. X is contained in the closure, and it's transitive. So, I mean, this is, I don't know, sort of basic, right? And it's a pre-geometry if it has exchange. And it becomes a geometry if points are closed. You quotient by the equivalence relation of closed points. And and this can also be, a matroid is a different way of formulating this same notion. And the real point of strong minimality is that you have a geometry in this sense, and then the Baldwin theorem says that the theory is controlled by a geometry. Now, quasi-minimal excellence. I've got this long. Andres and I wrote a paper expounding this a couple of years ago, and I took this long quote from him because I don't know, he insisted I was at this meeting, but I don't think so. So a group of people working in abstract elementary classes, including Rami, Monica Van Doren, Olivier Lesman, and Andres, were discussing excellence, this kind of diagram we were talking about, the amalgamation properties. And then there was a lecture by Zilber, and we all attended, not expecting to understand much. But at the end of Zilber's lecture, dealing with exponential covers, mentioning many analytic number theory methods that were arcane to us, mixing in such areas as never-linear theory, he asked a final question and drew a picture underscoring his question. And that's the picture. And And so, Boris's question was exactly about the behavior of the types in this diagram and how to control in small pieces in the components. We jumped to talk to him at the end of the lecture with the excitement of seeing a potential connection. Boris said he didn't know the model theory of L omega 1 omega, but he looked into excellence. After a few weeks, the first draft of a proof of the property of pseudo-exponentiation, drawing on a version of excellence and quasi-minimality in L omega 1 omega was circulated. And that's the, I mean, and so what Andres and I were doing in this paper was discussing the history of that for the next 20 years, which has had a lot of connections with number theory, and we'll see some of them. So let's talk about covering spaces of varieties arising from Fuchsian groups. So we start with trying to give some idea of where varieties and covering spaces come from. So it's an old subject. Diophantus asks about solutions of cubics. And in the late 19th century, they began to realize the right framework is in the complex numbers. And then a cube, these elliptic curves is a smooth projective algebraic curve of genus 1. Can be thought of as the classical torus. You have this picture where you mod out by the lattice generated by a particular set of generators. And so these things are quotients of the hyperbolic space by a Fuchsian group, and I'm going to define a Fuchsian group on the next page. And now we go back to Silber's dream that we should be able to get a picture of this in we should be able to find the logic where this is axiomatized and categorical. So a Fuchsian group, a couple of technical words. So a Fuchsian group, well, so if I just plain group theory, you have G, and we're working in some bigger model, some bigger group, may call it H just for the fun of it. And I have two groups, G and G prime, where G prime is the conjugate of G by some element sigma. And then they are commensurable if this piece has finite index in each of them. And then the commensurator is the set of gamma, the set of sigma that when you conjugate G, the commensurator of G in H is the set of sigma in H that when you conjugate you get something that's commensurable with G. And now a Fuchsian group is a discrete subgroup of PSL2 of R. And there are two such, it can either have infinite index in its commensurator or finite index. If it's infinite, then it's arithmetic and then it has all the ties to number theory. If it's not, well, I mean, in many places it's not, they don't care, but things like triangle groups, this is not a subject that's never been looked at. There's a small piece of this. And it's always the case that when you mod out the hyperbolic space by gamma, that is, you do two elements are equivalent if there's an element of gamma that takes one to the other. You get a compact Riemann surface, and it's an algebraic variety. I mean, that's again sort of our formalization business, right? That you have this compact Riemann surface, which is a very geometric notion, but given by a formal, well, by a discrete thing, right? Just like. And now, let's look first. So what we're going to be looking at are these covers, thought of as a two-sorted space. Here is what originally we would think of as being the hyperbolic plane, and here is C, and then the quotient. This is actually a fine point, but we're really looking at the variety, not all of C or all of C to the n in whatever dimension this actually is. And what is the structure over here? The structure over here is, this is a bunch of points. And we have, from the G that we're studying, functions f sub G, so that f sub g of x is gx, if we think about it, you know, tau g acts on it. But it's just, these are symbols in the language. You can't, well, you can iterate them, but you can't quantify over them. The group elements are fixed in the language. I mean, this is the way one does the module theory, the model theory of modules. You fix the names of the rings for this kind of things. Yeah? Oh, yeah. And now an element here is special if there's a G that fixes X. Right? Oh, no, it's not only that it's the fixed point, but it is, there exists a unique X that's fixed by G. And then it's a theorem that every element is either special, it's fixed by a unique element, or it's not fixed at all. So I said something that was true, but by accident. There are countably many fixed points. And so we're going to, when we build our models over here, the points here that are fixed, we're going to just put them all into the language. It's only countably many of them. This doesn't harm us at all. You might want to think about this in terms of the Zn. Is that, are we using it there? And we're also going to fix inside the field some countable model such that everything inside is definable over that field. Now that's a non-trivial fact for the arithmetic case that I'm not going to worry about. And in the image sort, this is C plus times, but also we Morleyized. Any relation in any n variables that you can define over the empty set or over these constants that I fixed, you just make be a relation in the language. So you have this quantifier elimination by fiat. And then the covering map is coming down here. Now, of course, what that means is when you, let's see, I guess if I take some partition here, these are the orbits, then all the elements in the same orbit will say. See, these things are just, I have learned these things in the last couple of years. They're not in my brain in the way that they should be. It's that you, well, no, that's the second point. The J function agrees on points if they're in the same orbit. Is that right? That's what I think I would say. And then the more complicated version, all right, so two things. Arithmetic is the same thing as having infinite index. So what I'm going to do is mention the work on the arithmetic case and then say something about how Juanina Blue and I varied that to do the finite case and why being finite is easier and gives you more leverage. And a key point is a result that goes back to Poincaré, that if you take a G, which is in the commensurator but not in gamma, then there's a non-zero polynomial, call it phi sub G in C of xy, such that for all z and h, the 2 points are agreed by the go to zero under the satisfy the polynomial, the point and its image satisfy this polynomial if and only if the j gamma is if and only if y is j gamma of z of hz for something in the commensurate in gamma g gamma. And now the crux of this thing is if you look at this map, and suppose you take some we take some finite set of points. I look at x, and then I have a g1x, a g2x, a g3x. I'm really listing out part of the orbit of x. And in the finite index case, that's going to stop. And in the infinite index case, it's not. But I look at finite approximations. And so if I look at this map up to some n, I'll call that map, what do I call it here? Oh, yes, if I think of a sequence, a finite sequence G bar, then phi G bar of x is the sequence of images. And clearly, if I look at that map, the image is definable in this whole language. But I've used it's the or p, whatever it is, p of g bar of x. So when I've got this p, then it's free. I know what the image is. It's definable in the language. The claim is it's definable in the field language. It's a subset of, and the proof is very complicated in the infinite rank case. I mean, they use some high-powered stuff. And, well, that's the way they did it. In fact, I think this argument works for both. By using Poincare, then it's easy, because this phi g tells you. And, yeah, I think it's kind of an accident that in Daw-Harris, and that's the principal source here, they used more power, but that's because they were working in class of Shimura varieties, and that was the natural way for them to do it. We didn't need that, and Bonnie saw a much easier way to do it. All right, now I'm going to try to tell you the axioms for this picture. And first order axioms, did I manage to forget the slide in the first order axioms? Wouldn't be surprising this morning. No. Oh yeah, right. So, well, the first order axioms are what I was telling you a minute ago, that you have this action of the group here, and you have the algebraic field, the algebraic closure. That's the variety in the field, and with these extra length, this extension too. And so you can just take the complete first order theory of the canonical structure in this language. And then the modularity axioms say that this really is a cover. If I look at this ZG, everything in it comes from a point, and everything down here that I define in my definition is, well, yeah, everything that's what I said. Everything in it comes from a point, and of course it is the image of those points. That part was part of the definition. And the special point axioms just say if G fixes 2 points, then they're equal. Right, that's what meant to be a special point, that there was the unique fixed point. And then you want to say that if you look at the pre-image of a point, the pre-image of a point, it's exactly the orbit. If j of x equals j of y, then x is one of the fg's of y. And the last axiom is that we want the field to be infinite dimensional. Right? We're looking at the the variety over an algebraically closed field, countable algebraic closed field of infinite dimension over Q. And now the argument is, now see these last two sentences are in L omega 1 omega. This is where we have to move into the larger language, larger logic. And then the theorem is that these axioms are categorical. And I'm going to say something about the proof because I think it will illustrate some of the issues we've been thinking about. And so the two main theorems are one due to Dahl-Harris and Terovitz gave another version. It's true for arithmetic groups and it's true for non-arithmetic groups. And the reason I think this is maybe interesting for this group is because of the distinction between the proofs. I mean, we've already made a distinction in the definition, right? We had this crucial point was a finite axiom, but we didn't really change the overall framework because the two infinitary axioms were necessary, and the idea of this G1 of x, G2 of x, etc. Row of G1, row of G2. That sequence was used heavily, but it didn't have a name. You weren't trying to axiomatize. All right, so what does finite index do for us? So what we have is here's this H, and here are G and G sigma and G intersect. G intersect G sigma. And so if gamma has finite index, then the commensurator of gamma in H is in fact gamma. I've actually the commensurator in G tilde. Well, what I'm missing here is this is taking place in what was the this is that's what I was calling. I called it H, but G, it's the enveloping group that we're working in. And it says the commensurator is the same. The commensurator of this G in here is going to be the same one as it is down where we are. And the second point is that if I have G is the commensurator in G tilde of gamma and the index is finite, well, that's what I just said. They have the same commensurator. Okay. And the key point, not from any deep mathematical reason, but in terms of how the argument works, is that the argument for the infinite index case is only concerned with subgroups of this form. And in the finite case, there are only finitely many subgroups of this form. There can be lots of finite index subgroups, but there can only be a finite number that have this form. And that's somehow where you get the foothold. Well, now I want to talk about, yes, and now we'll get back to some more connections with what were going on yesterday. And I'm going to talk about back and forth in a slightly different way than Rodrigo did, and the partial back and forth is the same, but there's different frameworks. So rather than for say, I'm interested in a theorem of Karp. So we no longer have the restriction of finite. We have an infinite language. We have what was the other hypothesis? On functions. Yeah, there's functions all over here. Right. And so we're working in the, much more expressive language. And then we say, there are two structures are back and forth equivalent if the system of partial isomorphisms between finitely generated structures. So you take, what I'm going to do is work up through finite degenerated fields and have a back and forth between these fields, or actually between the structure over the fields. Right, and so then the back and forth notion is the same. But the proof will be, we're looking at these two models and we're going to just keep building extensions of the map, and eventually we run out of points and we've got the back. And so the domain has to be definable and closed, and the range. Okay, so yeah, well, I've just, maybe somebody else has some other thoughts. I need to put these discussion questions before I give them game away. Yeah, I don't know whether anybody, it's, I mean, we don't have anything like these characteristic functions, the characteristic structures, and we're very much building with the big models. All right, yeah, all right, and then this is actually the theorem. So I say in L omega 1 omega sentence phi is complete if given any sentence psi, phi either implies psi or not psi. And Karp's theorem is that phi is L omega 1 omega complete is the same thing as all models are infinity omega equivalent. And so this is L omega 1 omega, this is infinity omega. And they are, and any pair of models are back and forth. I say quantifier free back and forth because of the treatment of Kiesler's treatment of back and forth in the 60s, where you have an existential back and forth, and then that gives you elimination. You don't get quantifier elimination, you get equivalent to elimination to sigma 1 formulas, and so on. That whole theory is sitting there. Yeah. Well, so phi is the axiomatization of the class.
Yeah, those properties are the properties of characteristic sentence. A characteristic sentence that it characterizes the back and forth equivalent class of some structure, if it is consistent. You have not put in your requirements that phi is satisfiable.
Yeah. Okay, but that's, yeah.
But if it is, then it defines the back and forth equivalence class of some structure, of any structure satisfying phi.
Well, it defines, yeah, but you have a sentence phi in L omega 1 omega. So it will in fact be L of 0 categorical. Well, I mean, we're showing that it's being a Scott sentence, it'll be L of 0 categorical. You may have lots of models up here. And then there's a, yeah, so I guess what happened, and we're saying that, yeah, on the class of all models of all structures with this language, then the L omega 1 omega class, this is the what this is one class of the equivalence under back and forth equivalence, or under having the same collection of sentences true of it.
Yeah, the class of models of phi is the class, is a back and forth equivalence class.
Yes.
A quantifier free back and forth.
Yeah, right, yeah. Right.
This is a characteristic formula, a characteristic sentence. That is the. That is
well,
it is a complete state. Is a complete back and forth state. But
I only know I'm certainly not what I'm confused about with characteristic is I can certainly write lots of equivalent forms of this sentence. It's not a fixed syntactic sentence.
Yeah. You have given just the characteristics. There are many ways in which you can construct characteristic formulas. We have discussed one way, but there are other ways to syntactically construct a characteristic formula. But that construction that we discussed yesterday applies to L omega 1 omega.
That is, you're saying that although I have many different equivalent sentences for this, you can provide an algorithm that will tell me this is the one that we actually want.
Yeah, it will not be completely decidable because it will depend on the model that you are trying to characterize the word.
No, but I take, well, but it depends on beyond its isomorphism class? I mean, I just.
Yeah, it depends on its.
Yeah.
Because you have to test it. Formulas are satisfiable. So it will not be completely effective. But I can do that in this model.
Well, okay. I mean, I just. I'm only talking about an isomorphism class. So you're saying that if I give you a structure, and I only care about structures up to isomorphism, then you can tell me the exact. You have. I mean, we know there are many formulas that work, but you have an algorithm that will give you a specific one.
Yeah, if you give me a countable structure. Yeah.
Yeah, and this, yeah, I think I only care about countable structures here, although I wouldn't swear to it. Right, and so this is really just being a little more explicit about what we mean about the back and forth, because the actual argument will be look at a family, look at two arbitrary structures, look at all the finitely generated subgroups, and build your back and forth going up the. Okay, so now what I'm going to do is talk about the proof in the finite index case, and as I do this, I'll make remarks about the infinite index case, which may or may not make sense since we haven't been discussing it. So So suppose I have a finitely generated field over which S and the ZGs are definable, the Poincare polynomials are defined. We add the coordinates of the special fields. So everything that I need, I mean, the main idea is everything I need is countable, so shove it all in. And now suppose I have two models, Q prime, Q and Q prime. Now consider the set of finitely generated substructures of Q and of Q prime, and the collection of partial isomorphisms such that if F is in I, the domain of F and the range of F are finitely generated. All right, so EAB of sigma is the field that we're talking about, that wherever which everything is defined. I mean, it just didn't get named up here. Typical member of the system has domain. So I'm looking at a U and a well, yeah, somehow or the other here. Here was Q and Q prime. Oh, and now it's U and V, I think. So, but we look, the domain of F is one of these models, which is a union of the domain part and the variety part. Since U is finitely generated over L, first it's the finite, it's the G orbits of a finite number of elements in the domain. So maybe I can say something sensible with a picture. We've got two models, and now we have finitely generated submodels. Right? And each of them will have a kind of a, this is D and this is S. I've got two finitely generated submodels, and then I take an extension of this one, and I've got to find an extension of this one that is isomorphic. And so here on this side, there's some finite number of additional points. And yeah. And so when I'm trying to find this, right? So here there were a finite number of additional points. I can choose them here. And maybe I'm doing it one at a time. I'm not thinking about it right now. But probably I am. Just look at a one element generated extension and then take one here. And off to the side, I mean, this is a kind of a subtlety. I'm not sure if we really want to get into it, but this was something that the geometers just sort of didn't think about. They said, well, we're going to be working over this field, this LU that I'm talking about, but it ain't there. The domain of this structure is S of U, and so one has to observe that if you look at S of LU, it really, everything that's here, this is a basic fact about stable theories, that definable, you have a definable formula in a stable theory. So here is a model of a stable theory. Here is some definable subset. It has this certain parameters. And now you take some other definable formula. This intersection is definable by adding parameters in here. And this is, this is one of the foundation stones of stability theory going back to 69. But that's what we do here. So we realize we can do this, and so I can put my parameters in the field. In the variety. So that's it. UD consists of G orbits of a finite number. US is the field on the other side. The additional points determine only finitely many new field elements since it's constant on each element. The field remains finitely generated. You make a similar system for the other one. I have some stuff here, and then I copy over here. And if I have the isomorphism over the small pieces, then F restricts to a G equivariant injection of UD into U prime. Remember, U is the big set. I'm trying to build these small models. And so I have some bijection over here and no, injection over here, and then I extend this by what I take. I mean, but I know I can find the points in the big model, and then I add. But then there's only finitely many of them, so I extend the small piece by this. All right. Oh yeah. Okay. So now there's a reason that I want to say something about this next step. And that is, how are we going to define, how are we going to pick the image? I've just said I can do it, but I was actually lying. I was saying that's what I want to do, and I want to say something about why I can do it. And the key point is this new notion. I mean, so this again is something where Daw and Harris, well, they used the word determines, but it wasn't quite clear what they meant. And what do I say? I say that if I have an A contained in M, which are both models of the G. It's just so I have some big model dm, and here's dA. dA is here. And I look at, no, and then there's the other side here, right? Here's the SM, and some SA. So if I take a D here, and a B, those boldface means that I have a finite sequence. We say that the quantifier free type in tau S, so here again is where we're being very careful. Tau S is the field language. So I look at this point over here, so it's quantifier free type of B, I hope. Well, J of G check of D. So I'll say in a minute what exactly this means. And B. So B is some new parameters down here. And J of G check is back here. Here's D. G check is this finite sequence of images of G1 of D, G2 of G, and then you apply we've called it J there, but in the rest of this talk I was calling it P. It's some element down here, and what we're looking at its type over what we know so far. Now, and then the claim is that if I just look at this, it tells me the entire type in tau of dB. And the difference with the arithmetic case is that instead of having J of GD of bar, they have J of G1, G1, G, G2, D, the whole infinite sequence. And of course, from a model theorist standpoint, we've suddenly become not so much under control. And so here here we can be very precise, but it also sort of clarifies what you're doing in the other case.
John, maybe there's a missing B in J, G, check E, B. In the last sentence, if J, G, check E, B after E, after the parentheses. Because,
yes,
because you say nothing
right.
about B in this condition.
Yeah, that's right. But this, yes, okay, right. You're right. Thanks. Right. Yeah, right. Yeah, that's exactly right. Yeah, what's in, yeah. I mean, yes, that's the right hypothesis. And the thing that we're showing is that on this side we just have tau. But we're getting the here on this side we just have tau s, and on this side we have tau. So that we've managed to learn everything that this function, this J function is telling us. And oh yeah, so this is what I said a minute ago, because as usual I can't remember what my next slide is. They are able to get back to a finite sequence, but they're using very high-powered stuff. That it's been 2 years since I was talking about this stuff, and so I don't even remember what the names of the theorems that I didn't know that I didn't understand were. Okay, and then you prove this back and forth. I've sort of given you the steps for being able to prove it back and forth. And now, the gain is, I'm going to say, at this point in the arithmetic case, they say this first sentence. It's axiomatized by a complete sentence, Scott sentence. The restriction to a first-order theory, which I'll probably have this on the next slide, is quantify or eliminable. But they don't know anything about the omega stability. They're going to go ahead and eventually prove the categoricity, and then you can conclude the omega stability. But here, because we've got this finite string, we can just read off the omega stability. The image is sitting in an omega stable first-order theory, so it's omega stable. And that's the crux of why there's one more heavy algebraic thing that we do much more easily because we have the omega stability. All right, so this tells us that the unique countable model of this theory is axiomatized by a complete sentence of L omega 1 omega, it's Scott's sentence. And the first order theory is complete. I told you I was going to say this, and admits elimination of quantifiers. So we've gotten to have a complete theory, but we're a long way at that point from saying it's categorical. And the essential point is that in the arithmetics case, you've got lots of finite index subgroups, and you have to handle them. You have to look at the inverse limit of these structures, and the geometers have the theory for handling those, but we'll avoid it. So it's just well, we've made a huge assumption by saying it's finite index. We'll get some leverage out of it. Now, I want to go back a little bit more to what the actual definition is here of an almost quasi-minimal excellent class, which will yes, so this is the framework that Zilber starts with, and it's like the Shalas situation in that there's no syntax here, right? It's a property of structures. And, well, there is syntax, but there's no, what do I want to say? Yeah, no, that was just wrong. We aren't, it isn't as abstract as an abstract elementary class. What it is it is an example of an abstract elementary class. You have a definition of a pre-geometry on, you have this closure relation which defines a pre-geometry. And the closure is in fact a member of K. And now this is the crucial point. The countable closure point, the closure of a countable set is countable. Now when I say that's crucial, it's because for Zilber, that's why he has to have the L of Q1 in his axioms. And it's the difference between the exponential case and the covering of the plane, because when you're covering the additive group, then you get finite index for free. You get the countable closure part, and so it's in L omega 1 omega, while the exponential is in L omega 1 omega of Q. All right, and then you have two properties, L of 0 homogeneity over the empty set, which is actually what I just proved, right? That all the things are open. And then L of 0 homogeneity over countable models. Right? Yeah, for either the empty set or a countable model. And in these examples, that's a big difference. So that this, we've done this much so far, and this one is another. We'll appeal to some Sarah and blah blah. And this kind of stuff that I'm blathering about now is laid out more clearly in my paper with Andres. That's in the journal Model Theory. And now, it's an almost quasi-minimal, and I say almost because Zilber's original idea was quasi-minimal means every definable set is countable or co-countable. And it's just, it's not true here because we've got two sides of the universe. But what is true is everything is in the algebraic closure. If you take a maximal independent set, then its closure will, every element is in the closure of any maximal independent set. That is, I'm going to have a basis on this side, I'm going to have a basis on this side, but the maps between them are finite to finite. So either one of them will serve as a basis for the whole thing. But I just wanted to preserve Morris's original notion because there are places where it's used and they aren't the same thing. Right, that's just what I said. And it's, partly because that was what the notation I used in first order. So now what's left is to prove the quasi-minimality that you I think the only hard part is, right. We have to get from this homogeneity over the empty set to homogeneity over countable models. And the crucial point for this, yes, the quintuple paper B is Bayes. Hart and Houtanen, and oh, it should be BHHK. Oh, maybe that's why it's plus. Bayes, Hart, Houtanen, Casala, and Kirby. So this was at some conference in Germany, I think, that these people worked this out, and they really gave a much cleaner formulation of Zilber's theorem. And in particular, they get this condition. If I want L-zero homogeneity over models, I just have to prove that if I have something up top, then there's a finite subset of X, so the type of A over M does not split over X. I'll tell you what that means. And presumably I'm going to have that on the next slide. And if I don't, all right, so I need to put the definition of it. The type of A over M does not split over X contained in M if there does not exist, a pair of elements AB in CD in M such that C and D have the same type over X, but there is a phi such that phi of AC and not phi of BC. So you can't have two formulas, two constants realizing the same type that distinguish the points. And again, this notion of splitting is in the very basis of stability theory. It's in the earliest papers. And here is where it becomes useful. And then so the main result is if it's causing I think did I just not? No, I didn't. Okay, so I'm just restating it there. And the arithmetic case has a this they call it I don't know. I can't remember what the I stands for, but an FIC1, finite index condition 1, and it's this sort of things. And a second finite index condition here, and here again we're using some powerful stuff, and in the finite case we're going to avoid it, which I hope I didn't write it down. The point is that this property of not splitting is just true in an omega stable theory. A type does not split over a finite extension. And so we just plug that in, given that we know the theory is I'm probably lying a little bit because I think this proof is a half a page long, but that's the key point. Okay, and now I just end with this. It again is from our paper with Andres, and we late enough that we put the paper with Bonnie in. But you take these various notions of what kinds of notions of covering that come up in number theory and algebraic geometry. So, one is complex exponentiation, and that's this big question about, well, we have a nice theory which is categorical, but maybe the complex numbers don't satisfy it. I mean, McIntyre, for instance, works very hard at trying to prove it doesn't do it. And then you have the covers of multiplicative groups. and then the J function, that's just sort of background for the subject. Modular and Shimura curves, again, these proofs are pretty much the same. But when you ask, when you move to a billion varieties for, well, one case is finite Morley rank groups and the other is finite Morley rank plus no top. And then they have to use stronger methods. This no top is one of the steps in the main gap, and Brad Hart really explained what it meant, and so he's one of the. I think this is Bayes. I don't know. Hart. It'll come to me in a minute. Anyway, they're using different methods, and because of higher, I mean, the difference is that these things were just binary. They were working as curves, and when the dimension goes up, then these kinds of notions have to come in, or at least have come in any proofs that are known. And Boris has a more general argument for smooth varieties. And I think, yes, okay, so we have half the references here. I will give this to you tomorrow after I get the references correct. And the rest of them. So, any other questions or comments? Well, what I've I'm not sure how this seemed more relevant as we were going through that these issues of what we use these more complicated logics. Well, why? And well, I mean, one natural question is, does all of this sort of work out in the end? Right? There's a lot of hidden algebra, and maybe that doesn't matter, but just even formalizing the stuff.
Yeah, I think that you are defining a structure with by giving a categorical or aiming to give a categorical theory for it, but this is a kind of definition that lies within ZFC, and you are defining a class of structures which can be seen as a predicate. The class of structure contains only one structure up to isomorphism, and the definition can be written down. It is the case that definition uses so there's L omega 1 omega sentences, but that can be done within within ZFC or ZFCN. But it is really a question that interests me the most, which mathematical notions really require this step to infinitary, or at least omega 1 infinitary.
Yeah.
This is, I think this is great. You have given some notions in elementary geometry now in geometry of complex numbers, algebraic geometry, and this is, I think, is an absolutely important project.
Yeah. So that, yeah, and that to that, if we just go back to the axioms, that was the. Yeah. So the crucial points are these two. That's where the L omega 1 omega is being used. And I guess this one is sort of analogous to in the to what Zobo did in the covers of the fields, where you said that the kernel was fixed. Wow. This. Well, oh yeah, no. I mean, this last one about being infinitary is just. If you didn't have that, you would have the things of finite dimension, and so it isn't going to be countably categorical, and that isn't really a big deal. It'll still be one categorical, but you won't have one theory. You'll have a theory that says I'm of dimension n, and this is stuff that's over and the 5 people. I want to thank you all. It's been a very pleasant week, and I've enjoyed talking with people. We'll continue.
Minicursos, and unfortunately the last lecture. Thank you.
Thank you. Thank you. So we are highlighting some important points in first order definability theory that are also useful for L omega 1 omega also definability theory, which is back and forth constructions, as we have seen in the lecture, previous lecture by John. And today I will present some stuff that does not pass to the infinitary case. So let me recall that we ended up with these two very basic results, and well, basically compactness does not pass to omega logic or L omega 1 omega setting. Downward Löwenheim scaling is okay, but this is not, and this will be important today. So now let us consider another notion that appeared in the in John's lecture that I call delta equivalence. Right? It is the idea that the idea of a basic logical equivalence restricted to delta. So we say that two pairs structure, tuple, structure, tuple are delta equivalent if and only if they agree with respect to the delta formulas, or if the type of A bar intersection delta equals to the type of B bar intersection delta. So delta is a set of sigma formulas closed under negation. I put this condition just to it is convenient, and such that no variable other than x1, xn is free. So that is it. We say that A bar, B bar are delta equivalent if and only if for every phi in delta, A bar satisfies phi if and only if B bar satisfies phi. It is a natural notion of logic equivalence restricted to delta. Elementary equivalence is a special case in which delta is the set of all formulas in these variables. So A bar and B bar have the same type if they are delta equivalent, if delta is the set of all formulas in this in those three variables. So we have a kind of disjunctive normal form lemma in first order logic. Yesterday we discussed something which is very close to this when we were talking about the characteristic formulas. We made the disjunctions of conjunctions of formulas negated or affirmed, and this defines all first order formulas admit some disjunctive normal form in that way, but I will generalize that kind of result using the notion of determination that appeared today in John's lecture. So we have some formulas, and we may even change the signature at some points, and we have some formula psi, or a set of formula psi, which are determined by delta, right? Like a type in a smaller signature can determine the type in a larger signature. So let T be any first order sigma theory, and delta be a set of formulas closed under negation and in x1, xn. Let psi be any formula, not necessarily in delta, in x1, xn, right? So assume that psi is determined by delta. What does this mean? This means that for all models A and B of T, and all tuples A bar and B bar, if they are delta equivalent, then they agree with respect to psi. So we say that psi is somewhat delta determined, right? The properties in delta satisfied by an arbitrary tuple in a model of T determine the satisfaction or not of psi. Right? Under these conditions, psi is a disjunction of conjunctions of formulas in delta. So this uses compactness twice. The proof of this is based on compactness. Well, so this is an important definability result, because psi is being defined in terms of delta, right? So maybe delta is a formula in a signature that is less than sigma. And so psi is being defined as a disjunction of conjunctions of formulas in delta, which is an explicit definition of psi in terms of the predicates in delta. Now let me say something about this compact regular logic. Well, this is the kind of thing that L omega 1 omega is not. For every signature sigma, a regular logic provides a set L of sigma. So an L logic, a regular logic L, can be thought of as a function of signatures together with satisfaction relation between sigma structures and sentences satisfying some property. So this function L assigns to each signature a set, an arbitrary set. I'm not saying what set is this, that we shall call a set of the set of L sigma sentences. The idea is that this set is the set of sigma sentences in L, but it is an arbitrary set. We are not saying what is the syntax of L, what are the grammatical rules behind this set. And a satisfaction relation in more or less the usual sense, right? That a first order structure may be with a particular sentence of the signature sigma. And we ask that the satisfaction relation is preserved under taking reducts, isomorphic copies, and the sentences in this logic can be relativized in the way that we were discussing yesterday with respect to any unary predicate. Right, not in sigma, and each L sigma, although L sigma has no syntactical structure, is closed under semantically under negation, conjunction, and disjunction. What does this mean? Right? For every sentence phi in this set, there is another sentence psi that behaves like the negation of phi. And for every two sentences phi and psi, there is a third sentence gamma, which behaves like the conjunction or the disjunction of the given two sentences. So a compact regular logic is a regular logic such that it is compact. Every finitely satisfiable theory in this logic, a theory is any set of sentences for a fixed signature, has a model. So if you have a theory and you want to know if that theory has a model, it is enough to show that all its finite parts have models. Yeah. No, just fails compactness. It is regular. But omega logic fails regularity because omega logic does not have relativization. It cannot relativize sentences in omega logic. It will not work. Such a logic extends first order logic if every first order sentence has an equivalent in L in the same signature. So let me state another lemma, which is very important. I don't know if these, just like the lemmas that I have stated yesterday, the codification of isomorphisms or partial isomorphisms, they are surely present in some form in the literature, but I don't know who first used this this kind of thing. Maybe it's Venonius, I don't know. And I have never seen these results explicitly stated as lemmas in the literature, but maybe there is in some of the some paper, but I don't know. Anyway, I have attributed it to Lindstrom because it is implicitly present in the proof of Lindstrom's first theorem. So let L be a compact regular logic extending first order logic, and sigma be a relational signature, sigma 0 a subsignature that is finite. Let phi and psi be sentences from L of sigma. So we are going to see a situation that is close to the ones that I have been discussing yesterday. So it formalizes part of the discussion that we had yesterday. So assume that for every natural number p, there are sigma structures A and B such that A satisfies phi, B satisfies psi, and whose reducts to sigma 0 are P equivalent. It follows that there are sigma structures A and B such that A satisfies phi, B satisfies psi, and whose reducts are sigma 0 partially isomorphic. So let me recall that yesterday we were discussing the codification of this kind of thing. We want to codify, I will ignore the tuples for the moment. We want to codify the existence of isomorphic or structures with an isomorphic reducts satisfying some conditions. So in this case, A satisfies phi and B satisfies psi. This is the additional conditions in this case. Those are the additional conditions. But we want to show that there are structures, sigma structures, verifying this. So how do we do this model theoretically? We codify this situation in a theory, right? So I have shown those theories TF, sigma 0, sigma, with possibly with tuples, but in this case I will ignore the tuples, right? And a model of this theory contains unary predicates, which are domains of models, and it contains a relation between those predicates, which says that they are isomorphic. In general, to prove that first of all, to accomplish this, we must or we can prove that such a theory is consistent, right? And then it has a model, and the model gives you the the existence of the structures and the isomorphism. But with the additional conditions, right, we must extend the theory. So we consider now this, that phi holds when relativized to U. And psi holds when relativized to V. Right? And then if you show that this theory is consistent, then you have shown this. But this is hard to achieve directly in this way. So how do? We first prove that this theory, it is a different codification, right? So we use the partial isomorphisms, and here is I, right? And this is a theory with an infinite number of axioms. And we show that this theory is consistent. And to show that this theory is consistent is to show that the finite parts of it are consistent if we are in a compact logic, like this one. And as it happens, the finite parts of this theory can be shown to have a model if we have this for all P, which is still weaker. So that is what is happening here. We assume that for every natural number P, there are sigma structures A and B such that this happens. So this assumption says that the finite parts of this theory are consistent. But we are working in a compact regular logic. And so the whole theory is consistent. And it extends first order logic. So what does it, why we have added this extension property? To guarantee that this theory is an L theory. Because this theory is first order theory. Except for this part, because phi and psi can be in L. They are not required to be in first order. So this is an L theory, because this is first order, and L extends first order, and this is in L. Therefore, the assumption guarantees that all finite parts of that theory are consistent. It follows that there are, it follows that the whole theory is consistent, and so there are sigma structures A and B such that A satisfies phi, B satisfies psi, and they have partially isomorphic reducts. This already proves a form of Lindström's theorem. So if we have here in the notion of regular logic. The preservation under partially isomorphic copies of structures, right? If we strengthen this requirement that the satisfaction relation must be preserved not only by taking reducts and isomorphic copies, but this satisfaction relation must be preserved under taking reducts and partially isomorphic copies of structures. Then in this stronger notion of regular logic, we have a Lindstrom theorem already with this lemma. So first order logic is the only compact, strong regular logic extending first order logic. So it is a maximal, compact, strongly regular logic in the sense that I have said above before. Why this is so? Because you can prove that if phi, for example, is a sentence that is not first order but is in this hypothetical compact strong regular logic extending first order logic, if phi is not first order, then phi is not preserved under p equivalence for any p because of what we have seen yesterday. That Freire's definability theorem. If a predicate is preserved under p partial isomorphisms for some p, then it is definable by a formula with quantifier rank p. So if phi is not definable by a formula, by a first order formula, then it is not definable by a first order formula of quantifier rank p for any p. Therefore, we have, this means that phi is not preserved under p equivalence for any p, but this means that for all p, for every p, there are sigma structures A and B such that A satisfies phi, B satisfies not phi, and such that its reducts are to the signature of phi, to the signature, finite signature of phi, are p equivalent. Right? Therefore, there are sigma structures A and B such that A satisfies phi, B satisfies not phi, C here is taken to be not phi, and whose reducts to the signatures, finite signature of phi are partially isomorphic. But that is absurd because the satisfaction relation is supposed to be preserved under partial isomorphism. So A cannot satisfy phi and B satisfy not phi. And at the same time be partially isomorphic. So we can have many other results like this, right? By these lemmas, which are not very difficult. We don't need Löwenheim-Skolem here. Löwenheim-Skolem is used to get an isomorphism from a partial isomorphism using Freire isomorphism lemma. And this is what you get in this case. So let L be a compact regular logic extending first order logic. Assume that any satisfiable countable theory has a countable model. This is the a version of the Loewenheim-Skolem property. Let phi and psi be L sigma sentences and sigma 0 contained in sigma be a finite signature. Suppose that for every natural number p there are sigma structures A and B whose reducts to sigma 0 are p equivalent, and such that A satisfies phi and B satisfies psi. The same assumption as before. But now it follows that there are sigma structures whose reducts to sigma 0 are isomorphic, not only partially isomorphic. This is because we get now the Loewenheim-Skolem theorem, and this theory is countable. This is a countable theory in L. So we get these structures, these isomorphic structures, such that A is a model of phi and B is a model of psi. From this we get Lindström's first theorem, which is just a formalization of what we were talking about yesterday. This is the 11th lemma. So we have 11 lemmas in definability theorem. Let me recall all of them. This is the first lemma. If two structures, in fact we are talking about pairs of structures and tuples, but let me say just structures. If two structures are P partially isomorphic, then they are logic equivalent up to rank P, or they are delta equivalent if delta is taken to be the set of all formulas with quantificational rank below P. This is the second lemma. The converse. If two structures are delta equivalent, in which delta is the set of all formulas with quantificational rank at most P, then these two structures are P partially, right? Third lemma. Any predicate whatsoever in any class, which no condition on the class, it is not required to be first an elementary class or stuff like that, or an abstract class, nothing like that. For any predicate in a class, this predicate is explicitly definable if and only if it is invariant under P partial isomorphisms. Fourth lemma. It is Freire isomorphism lemma that we are using here. If two structures are countable and partially isomorphic, then they are isomorphic, succinctly. This fifth lemma, the isomorphism characterization lemma. There is a theory, right, characterizing that situation for isomorphisms, the existence of isomorphic structures. The sixth lemma is the same thing for partial isomorphisms. there is a countable first-order theory codifying partially isomorphic structures. 7 and 8, compactness and Löwenheim schooling, downward Löwenheim schooling. 9th lemma, the disjunctive normal form lemma, right? If a formula psi is delta determined, then it is a Boolean combination of delta formulas. 10 and 11 are these Lindström's lemmas. Lindström's separation lemma, it says that if the classes of models of phi and psi cannot be separated by classes of p equivalents, then they cannot be separated. The classes of models of of phi and psi cannot be separated by classes of partially isomorphic equivalence classes. Class of equivalence under this equivalence relation. Right? It is a separation lemma, right? It means that there are this existence of A and B. This A and B are, one is, yet here the models of phi, and here are the models of psi. The intersection means that here we have a structure A, and here we have a structure B, such that they are related by the partial isomorphism relation. So if for every P this happens, there are structures A and B, P equivalent, one on this side and the other on this side, then this happens. And Lindström isomorphism lemma, separation, and yeah, well, this is intersection, this is in separation. That is, you cannot separate this class of models from this class by equivalence classes of this relation. Because any equivalence class of the equivalence class of this structure also contains this, and so there will be an equivalence class that is intersecting both classes of models. In the case of intersection, there will be an intersection indeed, because A and B must be isomorphic, and so it means that the picture is like this, because they must be both in the two sides. There will be an intersection of the classes of models. Well, the aim now is to show Beth's definability theorem, right? I will not be able to give, probably I will not be able to give the complete proof of this, but we can discuss the hard part of the proof. Beth's definability theorem, and more importantly than discussing the proof, is understanding what this result gives us. So I have argued in the conceptual part of this work that implicit definability is the basic definability notion. That means that we should take implicit definitions, let me use that expression, as the primary mathematical definition notions, right? So those are not arbitrary games, right, on definability and so on. This provides a theory of mathematical definitions. What is a mathematical definition? So this is the question we are trying to answer. So I have argued that partially a mathematical definition is an implicit definition. Well, if mathematical definitions are implicit definitions, and if we are working on a background first order theory, then these definitions can be given an explicit form. This is what Beth's theorem says to us. But also the relevance of this is that, and if we are not working on first order theory, but on as I have also argued, on a omega logic theory, then can we have also some kind of explicit formulation of our definitions? That is, the implicit definitions admit some explicit form, and this is important because if it is like Hilbert's, right? Hilbert's program for the foundations of mathematics was conciliatory program. So he told us, well, even the intuitionists will agree with us or can have a life in our program by just forgetting about the interpretation and constructing the proofs syntactically. So it is a constructive activity because it is pursued in the meta-mathematics, which is constructive. So yeah, you are just constructing these syntactical proofs, the syntactical sequences, and the intuitionists can live with us, even the finitists can live with us, but the classical people are those that think that we are indeed pursuing mathematical knowledge. So that's more or less Hilbertian picture that tries to be somewhat neutral. There's some kind of neutrality. This is what one reading of Hilbert's program is trying to achieve some kind of neutrality between Platonists or intuitionists. In our case, to accommodate those finitist people, not that I'm very much concerned with them, right? I usually forget about those. But in order to accommodate those people, the agreement that I am proposing can include these people also. for our implicit definition, admit a syntactic version. So you can forget about the interpretation and work with the formulas of the definition, and that's okay. You just forget that this is a definition. Just forget that you are identifying some predicate. You forget about that. It's just symbolic game, right? In Hilbert's tradition, we are not concerned with models and stuff like that. No, okay. Yeah. So it would be important to have a kind of Beth's definability theorem also for omega logic. And this can be achieved by some of the results John showed to us, basically the Chang's result, that we can translate L omega 1 omega to omega logic, and also Beth's definability theorem for L omega 1 omega, which is based on the interpolation theorem for L omega 1 omega. Now we can prove Beth's definability theorem by the interpolation theorem, and the interpolation theorem can usually be proved by Robinson's joint consistence theorem. The point is, the interpolation theorem and Beth's definability can be transferred to the L omega 1 omega setting, but Robinson cannot. Robinson is very much compactness. So it's compactness all the time. It is a strong form of compactness. The proof I gave here is based on Robinson, just to highlight that, because highlight the difference between this case and the other case. So let T be a set of first-order sentences, a first-order theory in the signature sigma plus R. Recall that T and phi explicitly define the n-ary predicate R in terms of sigma and over the class of all first-order. We are in the first-order setting here. Over the class of all first-order sigma plus R structures, if and only if phi, with its variables displayed here, is a sigma formula such that phi is equivalent to R under T, right? This is to say that phi explicitly defines R. So R is explicitly definable if there is some defining formula defining R explicitly. Beth's theorem says that R is explicitly definable if and only if it is in terms of sigma and in T, if and only if it is implicitly defined by T in terms of sigma, that is, for all models A and B of T, the predicates RA and RB correspond to each other by the isomorphisms between the reducts. So this is how we can read the uniqueness condition. If the reducts of these models are to sigma are isomorphic, then the structures as a whole are isomorphic. The isomorphisms between the reducts also preserve predicate R. Right. So the proof of this theorem uses the disjunctive normal form lemma that we have mentioned, and uses basically everything that those 11 lemmas basically. We need to prove that if R is invariant under isomorphisms, in the sense this is an invariance of R if the predicates correspond to each other by the isomorphism. That it means that the isomorphisms between the reducts preserve R. Right? They are not required to be an isomorphism with respect to R, but they are indeed isomorphisms with respect to R. This is what it means to be implicitly defined. Another way of saying this is that the predicate R is determined by the other predicates. You cannot change this predicate keeping the others intact. You cannot change R and keep the rest of the predicates preserved. So we need only to prove that if delta is the set of all sigma formulas, then R is delta determined. R of x is a delta determined formula in T. And then we can apply the disjunctive normal form lemma. So this proof begins with compactness, because the disjunctive normal form lemma is proved using compactness 2 times. So this kind of proof will not go through L omega 1 omega. Completely different kind of machinery must be worked out. However, it turns out that it can be worked out. And this is where our new hero arrives, thinking. So Freire is the figure behind this first order definability theory. Omega logic definability theory is based on the canonical model construction, not on back and forth. Although we have back and forth in L omega 1 omega for order poses, it will not give us BAF. So suppose that R of x is not delta determined. This means that there are pairs of models of T and N tuples, right? Such that satisfying the same formulas in delta, that is, the same sigma formulas with variables in x bar, and such that A bar is in R and B bar is not in R. A bar satisfies the predicate R, B bar does not. Right. This is what it means to say that this formula is not delta determined. So let gamma be the type of this A bar intersection delta, the type in the signature sigma, that is. And it is the same for B bar because they satisfy the same sigma formulas. And let TA be the theory T plus gamma, which is this the sigma type of A bar, which is also the sigma type of B bar. T plus gamma plus R of X affirmed. The pair A bar is a model of this, because A is a model of T. Gamma is the sigma type of A bar, so it is satisfied by A bar in A. And R of X is satisfied by A bar by assumption. This is our assumption. So let R prime be another, make a copy of R. So make a copy just to distinguish, and replace R by R prime in T. So we obtain T prime. T prime is the same thing as T, but instead of writing, everywhere where you find R, you put a prime on it. So formally it is a distinct thing, but is semantically it is more or less the same thing. Gamma does not contain R. And add also the negation of R prime of X bar. So this is what T prime is. B bar is a model of this theory. B is a model of T. Now I'm just taking R prime to be R. So B is a model of T prime. Gamma is the sigma type of B bar, so it is also satisfied by this. And not R prime is satisfied by B bar, because R prime is just R with some mask, some and this is our hypothesis. B bar is not in the interpretation of R, which is the same as the interpretation of R prime. Moreover, these theories are jointly consistent. TA and TB are jointly consistent. For otherwise, there would be a formula theta with 3 variables, right, in the list, such that TA forces theta and TB forces not theta. However, TA and TB have exactly the same sigma formulas with those 3 variables, because theta would be in the intersection of the languages, and the intersection of TA and TB does not contain R, because TA is formulated with R and TB is formulated with R prime. So that is what this prime trickery is about, to eliminate R from the common language. And so sigma formula theta cannot be such that theta is valid in TA and not theta is valid in TB, because TA and TB have exactly the same sigma formulas, because they are gamma. Gamma is a complete type in sigma, complete sigma type of A bar, which is the complete sigma type of B bar. Therefore, from compactness again, so we have used compactness if many number of times. This has a model. The total sum of the theories has a model. Let this model be called C. C interprets both R and R prime because it is in the total language. So let D be the reduct of C forgetting R prime on the one hand, and let D prime be the reduct of C forgetting R on the other hand. Hence the pairs D C bar and D prime C bar satisfy TA and TB respectively. This is mediate from the definitions. Oh, this is just formality. Now forget about the primes. Right? So we have a model of the theory TA and a model of the theory TB. Right? That is, we have a model of, both are models of T, right? And these two models of T have the same reduct to sigma because they are both C reducted to sigma. So one is this one, that is the reduct to sigma of D is the reduct to sigma of C, and similarly for D prime. And so they are they have, this is D prime, right? But forgetting about the prime. So they have the same reduct to sigma. The implicit condition implies that they must have the same R, because they are both models of T. But this is impossible because C bar is here and C bar is not here. So this is a contradiction. With the hypothesis that R is not explicitly definable, but it is implicitly defined by T. So, well, I think I will not be able to go there, but yeah, maybe. What is the difficulty here? We have not proven the Robinson's joint consistence theorem. And how can we prove Robinson's joint consistence theorem? This way. Providing some isomorphism here. This gives you a proof. That's it. We have been discussing this. Lindstrom's inseparation lemma. There is let me try to sketch the argument. I will not go through this because I want to discuss some omega logic now in the end of my mini course. So Robinson's let me put back Robinson's here. If we have TA and TB jointly consistent, then the total sum of the two theories has a model. There is a strong form of compactness. we have two theories that are jointly consistent. That is, there is no contradiction in the common language. No, okay, theta and not theta. This is in the common language. Here is in another language. So we have here the language is sigma plus r. Here the language is sigma plus r prime. And here sigma. The language is sigma. Both theories are consistent. So both theories have a model. So we have a model of A bar of TA, right? And B bar of TB. We want a model of this. What we want to do? We want to sum up these two models, to make a sum of it, to amalgamate these two models in a model of the sum. But what is the obstruction to do that? Now, the obstruction is the common language. They may not agree. They are sigma plus r. This is sigma plus r prime, but prime is just a formality. The point is, their redux to sigma may disagree, right? This is a model of TA, B a model of TB. The situation is we may assume that TA and TB are just sentences because we only care about consistency, so a finite part is okay. But we may not have this. The reducts are isomorphic. Right. We may not have this. If we had the isomorphic reducts, then we could put these two models together because we would have no disagreement with respect to sigma. So pick a predicate in sigma. The interpretation in R is the same as the interpretation in B. So we can, in some way, some direct way, sum the model, amalgamate the models, and we will have a model of this. So the problem is just to construct something like this with isomorphism here. And in order to do so, Lindstrom's intersection lemma says that we are in first order logic here. So we need only to show that this theory is consistent. But to show that this theory is consistent, we need only to show that the same situation occurs with P partial isomorphism for each P. But this happens because these models are equivalent, elementary equivalent on the common part because they satisfy the complete, we may assume that these theories are sigma complete. This is not a problem. So that this holds, the P equivalence holds, and then we have the partial isomorphism situation, and then Lindström's intersection lemma gives us the isomorphism situation. This is used over and over again, at least in my account of the first order definability theory. Well, let us come back to omega logic to give a brief final overview of the resulting theory. So our goal is to, again, establish a reasonable theory of implicit definitions in the omega logic setting. By this I mean the notion of implicit definitions over the class of omega structures. We will not have explicit definability in the first order sense now, because we cannot have a single formula defining many predicates that I have mentioned that are implicitly definable in the omega logic setting. But it would be important to have, nevertheless, some kind of formalistic account of definitions also in this setting, because then the formalists could embrace our agreement, the agreement that we are proposing. We are proposing the following. Well, mathematical definitions are omega logic definitions. So this is now a new understanding of definitions. Well, formalists will only adopt this if they can have a formalist lifestyle within this agreement. But they can only keep their formalistic lifestyle if they have formulas to work with. So we must give them some kind of explicit definitions that correspond to our implicit definitions. Now, for us, for me at least, that I am not a formalist, the important stuff is the interpretative activity. I'm not a machine, right? I am a person, so I have perception. I have an interpretative unit. I will work with this. So for me, the important point is the identification of predicates, the identification of parts, important parts of mathematics, like the truth predicate or the standard natural numbers or whatever, the definability predicate, or maybe some of John's examples, the equi-decomposability relation. For me, this is, I identify this as an important relation in my life, right? But the formalist only cares about symbols, so we must give them symbols to work with. Give them some explicit form of the definitions. So in our agreement, don't worry, like Hilbert, don't worry, intuitionists. You can forget about the interpretation of mathematics. You are just constructing syntactical proofs, and this is the intuitionistic life. Well, the minimality of first-order logic. We have managed to prove some minimality results using that machinery. The minimality of first-order logic comes from Lindström's intersection lemma. I should mention it is a joint result, a joint work with Lucia. In fact, it is this that is used if we somewhat reverse, make an inversion, put first order logic in the place of L, and a sublogic of first order logic in this in the place of P equivalence here, because first order logic is appearing here. If you have some if you look at the things at some point, there are two logics here, not one. We have L and we have this P equivalence here. Well, this is delta equivalence for first order deltas. So first order logic is here. So we change this. Now first order logic moves from this to this point to this point. And this point becomes a sublogic of first order logic. And then we can prove that first order logic is the minimal logic satisfying Lindstrom. This is the proof that first order logic, this lemma in Lindstrom separation lemma is the fact that first order logic satisfies this property that I have mentioned. It has for every compact extension this holds, and it is the minimal, and it is the minimal logic that satisfies this. That is, if we put another sublogic of first order logic here instead of P equivalence, we cannot have the result, Lindstrom separation lemma, and we do not need Löwenheim-Skolem here. So if you look at this, first order logic is here, then it is a minimal logic satisfying this. For example, it is takes off some sentences of first order logic. For example, if you limit the quantification of rank, for example, this is a sublogic. Or if you take off some sentences, right? But the equivalence class of sense, right? No, because in this case we are working with a classical satisfaction relation. We do not change the satisfaction relation, but just take off some sentences. It is one example. This is an example of sublogic of first order logic, and the Boolean aspect must be preserved. It must be a regular logic also. This is a canonical example to stop at rank P, but there may be others. And take off some sentences with unlimited, keeping others with unlimited rank. In fact, the result is that you can take no one keeping this property. The property says something about all the compact extensions of the logic. Right. All compact extensions of first order logic are such that this holds, but for all compact extensions. If you take a sublogic of first order logic, this does not hold. Not all of its compact extensions satisfy this. There is a way to translate this. So, this is the minimality that we have managed to prove for first order logic, and I have managed to prove a minimality for omega logic that maybe can tell something about John's question of B interpretability between L omega 1 omega and and his omega logic, right? But this result is not hard, but yeah, if we omega logic is a minimal logic extending first order logic and categorically characterizing the natural numbers. That's the idea. So if you have any abstract logic, but be careful, as I have mentioned and John have already discussed this point with me many months ago, omega logic is not a regular logic, right? And so this is this minimality must be taken with a grain of salt. That is, it is not that is the minimal regular logic extending first order logic and characterizing categorically the natural numbers. The point is that any regular logic with these properties interpret omega logic, irrespectively of the non-regularity of the omega logic. So if there are some set of sentences categorically characterizing at least the domain of the standard domain of natural numbers, but then as John has shown to us, with a finite first order theory you get the standard model in with arithmetic. The hard part is to categorically characterize somewhat the domain, right? The countable domain. And suppose that the predicate n is not in sigma 0. So for each set T of sentences, there is a set T prime of sentences in the logic such that the omega models of T are just plain first order sentences. The omega models of T are exactly the reducts to this. The reduction here is projective, right? The reducts to this of structures satisfying T prime in the sense of L. So it is a reduction. So we have a theory T in omega logic. It is interpreted as T prime in L logic, in this L logic, extending first order logic and characterizing the standard domain. So we can indeed interpret omega logic in this logic. There is a converse of Chang's result. It is not hard. But an important case is L omega 1 omega. In this case, the reduction is not even projective. The reduction is direct. And I have here showed the reduction. Conversely, this is Chang's result that Professor John has taught us. Given a formula in L omega 1 omega, we can construct a set of first order formulas with the same free variables such that infinite, and I have refined this result for in some technical sense that is not relevant right now. And then I have proposed this notion of countable definability. It is a form of explicit definability, but instead of a single sentence, you basically use a countable set of, instead of a single formula, a single defining formula, you have a countable set of defining formulas. In the end, there will be a single formula defining the predicate. So let us try just to understand this, and then Beth's theorem holds for this kind of explicit definability for omega logic. So I will end with this definition. This definition is the important part of the work. So we say that R is countably defined by gamma of z bar. Z bar are the free variables here. Or that gamma z bar countably defines R in the class of all omega models of a theory, T prime, if conditions 1 and 2 below obtain. 1. Well, there is a set of sentences, delta contained here, implicitly defining the countably many new predicates. So gamma can contain new predicates, but all the new predicates introduced in gamma are defined in gamma by some delta. That is, if Q is a new predicate symbol occurring in gamma, one not occurring in our original language, then the predicate interpreting Q is implicitly defined by delta over the class of all sigma structures. And moreover, for any omega model of C prime, there is a unique extension A interpreting R and the new predicate symbols in the signature. Let's find delta. So delta is the definition, right? And such that this holds. So A bar satisfies the formula R. So A bar is in the relation, the predicate R, if and only if A bar satisfies all formulas in the set gamma.
This gamma C bar A bar is the same thing. We often write that as just right. A bar, substituting A bar for Z.
Yeah, satisfying the A bar for Z. Yeah. Routable. So this is the idea that gamma is defining R. But gamma is not a formula. If it were a formula, it would be the usual definition. But it is not a formula. It is a set of formulas. So, and this can be given a more explicit form. This gamma comes from the Schenck's result, from the proof of the Schenck result. It adds new predicate symbols. It is a technique in infinitary logic, the technique of expanding the signature of new predicate symbols designed to somehow capture the terms of a sequence of an infinitary formula. So the new predicates, you have an infinitary formula of phi 1, conjunction phi 2, conjunction phi 3. You add a predicate that captures phi 1. So this is basically the idea of the reduction. So I will end with this. The basic idea is quite simple, and it goes back, no, I don't know, at least it is very explicit in Lopez Escobar, but maybe before, I don't know if it's in the 50s maybe. If you have something like, well, let me put the disjunction here. Phi 0, let's see. Something like this. And suppose that each one of these phi is with a variable x. So we add a binary relation symbol, R, N, X, right? The idea is very simple, such that R0X is equivalent to this formula. R1X is equivalent to this formula. R2X is equivalent to this formula, and so on. And then, what is this equivalent to? To exist an n such that R and X, but this n must be standard. So this is a definition schema. This is a definition schema for R. Is it a legitimate definition? Well, only if this variable is allowed to goes through the standard numbers only. So that's why you have to have the standard numbers here. So you cannot write this, but we can write this. So this formula is the same thing, will be the same thing as this. Where this is the interpreted in omega logic. This gets interpreted in omega logic. We cannot allow arbitrary first order interpretations of this. And so we have now a definition of this formula. Let us say phi of x. Phi of x is just that stuff. But that definition is given by the addition of a new predicate and the predicates you had before in omega logic. However, this new predicate is schematically defined here. This is a definition schema, just like the definition schema of that we could 0 is the empty set, 1 is the unitary set of the empty set, and many others. So this kind of definition we can give explicitly. So the formalists will only be playing with these formulas in our game, in our agreement. We can give them a symbolic life for them to live. So mathematics is about the mathematical symbolism. I do not want to live without the symbolism. So take this symbolism and live under the rule that this is equivalent to this. It's a new agreement. Right? We have a predicate now to say that n is standard. Oh, use this predicate. Okay. Fine. From our point of view, we are interpreting things in the omega logic semantics. Right. From my point of view. Right? Then, under this countable definability stuff, we have a BEF, definability theorem for omega logic. This kind of explicit definitions. So this is This is the explicit definition in omega logic of this. The problem with this equivalence is that this lives in L omega 1 omega, and this lives in first order syntax. Right? But everything that you can define with a formula in L omega 1 omega, this means that you can define with this kind of formula. First order. Okay? So this is our main result in this definability, new definability theory. And then we can give a normal form for our theories for ZFCN. The normal form is just these deltas are just those schemas here, right? And in the end you have a formula phi star, with the phi star is this is phi, this is phi star. Phi star is the first order part. These are omega defined, is that so? So we have characterized the omega definitional extensions of ZFCN, and we need not to give up the recursive, so the formalist constraint on our formal theories, because those formal theories are recursively given. They are recursive schemas. If this sentence is recursively given, but in the important cases that we have mentioned, they are. So that is why Scott theorem does not play a role here. Why? Because Scott's sentences are not recursive, so they will not give rise to recursive schema, because this sequence is not recursive. It is given in terms of non-computable tests. So I have not put Scott's definability theorem, which of course is an important landmark in L omega 1 omega and omega logic. Scott was the advisor of Lopez Escobar, and they were working on this kind of stuff at the time. Scott also mentions this kind of reduction of L omega 1 omega to omega logic, but the details are in the Lopez Escobar paper. But then we need not give up the recursive axiomatizable omega definitional extensions of ZFCN, and they are strictly conservative in the sense that this kind of definitional extension is conservative in the strong sense that is important to us. That is, omega models are preserved by the extension, not just syntactical conservativity. Well, this is the end. That's why it is not working. Well, we must separate internal questions from external ones. So this the meta. So I am proposing this as a basic base theory, and this is not finitely axiomatizable, and you cannot replace it by a finite set of axioms, right? It has indeed an infinite, not only because of ZFC, it has an infinite signature, and axioms for each one of the symbols of the signature. So it is surely not finitely axiomatizable. But inside this theory, let us say, we can define the predicate of being a model of ZFC. And for this, we don't need the N, right? You can define the class of models of ZFC. K equals or of ZF, right? And this is a definition in ZFC also. It is a single definition here. ZFC defines the class of models of any theory. So because this is a set, so a single object inside ZFC set theory. So this is an internal discussion about models, and you can ask the external models, the models that are here. These are models that are, and this is somewhat related to John's frameworks. So the models of this theory are discussed in a somewhat informal framework, in a meta-theoretical or natural language, something like that. But internally, this is a single definition. So it is a single formula here. Yeah, but we do not have infinite formulas here, formulas that are infinite. So we have schemas, just like we have in ZF. In ZF already we have schemas. And in our new theory we have more schemas. But we don't have an infinite formula like this, or replacement which is like this. So we cannot write this down here. That is, you are saying we can give a definition of the replacement schema in this setting, and you were right, and that was one of the examples that I gave, that something is undefinable in the usual first order logic, and define what is undefinable. Is the proposition corresponding to schema, to the replacement schema. So the replacement schema is this proposition. You cannot define this in first order logic, but you can define this in the omega logic, but the definition will be another schema. So you are replacing one schema by another one, but in the end you have the definition. We can write it down. So suppose that this is the replacement, and it is recursive. This is recursive. And we do just some schema. Which now does not have free variable. Rn is defined, add this new predicate, so it will be a definitional extension, and this predicate must be defined. What is this predicate? R0 is equivalent to psi 0, which is the first instance of replacement. R1 is equivalent to psi 1, and so on. And what is the replacement proposition? Now, for all n, if n is a standard natural number, then R of n. This is equivalent to this in the sense of omega models. The omega models of that stuff are, and we do not need ZFCN to do this, it's just omega logic. You can state because it is first order. It's a first order axiom. The difference is in the semantics. Yeah, it is added. Yeah, the non-standard replacements. But the omega models of that together with this, the omega models of this plus this are the omega models of this. The usual models of this. So we have defined the proposition, and the same thing to induction schema or any other schema. And so this is. You cannot you have to add this to your logic. So in any case, it will be a not non-finitely axiomatizable theory. Yeah, to the interpretative side, but yeah, but we are not changing the symbolic life. The symbolic life is exactly the same that we had before. We were writing schemas before. We just continue to use those schemas and recursive schemas. Right. That's why I have not used Scott's theorem. I'm using only recursive schemas, and so we were writing this in the first place. So our symbolic life had no qualitative change. The change is in the interpretative life. But if you don't want to be interpretative in any way, you will not be interpretative in the first order also scenario. So the first order case also has many interpretative agreements. For example, you know very well, we can change the semantics. You work this out for ZF. And keep ZF with a completely different semantics. So why Tarskian semantics? Things came not from heaven this way. There is an agreement that the Tarskian semantics is the appropriate, implicit, tacit agreement that the Tarskian semantics is the appropriate interpretative life for mathematical logic, let us say. Well, now I am proposing to change this agreement. So, yeah, it is Tarskian semantics, but with omega structures, not general structures. You can have the general structure, you have lost nothing, because any general structure can be embedded in one omega structure. It is just that we always have this part of standard natural numbers appended that can be used if required. So you has lost nothing, just gained something. But this at the cost of an interpretative agreement that must be unambiguous. Do we have so the question is, do we have an interpretative agreement on the standard natural numbers? I argue that yes, because we have an agreement on the process of iteration, and that's what is behind this agreement. If we had no agreement on the process of iteration, we would have no agreement on what is this. On what is this. And this n is not required for this. Yeah.
So with CFC and now you can actually simplify a lot of things that you normally cannot do directly. It's here by, for example, defining
Definition.
yes, but also forcing. Forcing is in some sense a definition of truth. I mean, if you formalize the force relation, it's formalizable in CFC alone, and that's why you need the existence of model. So, for example, this is an easier kind of theory that we use for.
I don't think that it is maybe easier, but it gives you some simplifications. You were right. The forcing is a schema. We would better write this way. For each phi, we have a relation between conditions and individuals, right? So we have a schema definition, a definition by induction, a schematic definition, type code, schematic definition, and then we could have we could have a single forcing, but that would the definition of this would be based on those, just like the definition of this replacement is based on the instances of replacement. So this this definition would be based on the definitions of this still. So you would not eliminate this stuff, but we gain the possibility of speaking of a single forcing relation. That is what we are thinking. We do not think of one forcing relation for each phi. We think of the forcing relation, not a phi forcing relation. Yeah. Yeah, that irrespective of what meta theory. So in the same way that we speak of the replacement schema, not on phi 1 replacement, phi 2 replacement, or phi 1 replacement, phi 2 replacement. We speak of the replacement axiom or the induction axiom, not the phi induction axiom or the psi induction axiom as the induction axiom. We have the replacement axiom. It is this. But it does not eliminate the instances. You still have those infinitely many instances in your theory. Well. maybe the
Okay, again. At the very first day, you show a list of things that it would be nice to be able to define directly, exactly what we were discussing before. And these are all notions that are omega approximate, that you can approximate with an omega sequence of things, like truth with the complexity of formulas, or with schemas, again, with something very similar. So, and these are, I mean, I completely agree with you that these are very important notions and concepts in mathematics. Now the question is, I don't know, I don't have an answer to this, but can you think of notions that cannot be approximate with an omega sequence, but that still are relevant to mathematics? So the underlying question is, this is I'm completely convinced by this, but that the question is, do we really have to stop at omega, or are there some other notions that need some stronger logics or stronger agreements about?
Yeah, the notion of a real number, the continuum.
Yeah.
You can have kappa logic for any kappa. And the kappa logic, Chang's result actually is much more general, in that the L kappa omega can be interpreted in kappa logic.
Yeah. No, but yeah,
there are some conditions on kappa, but
as we know, of course, we don't have an agreement on the sides of the continuum.
Yeah, that's exactly the problem. The problem is not just logic.
Yes.
But because you could say, well, there is second order logic, our agreement. But
yes.
We have, this is to put, maybe to push our agreements too much. So,
yeah. But I mean, again, the question is then, of course, I mean, the continuum is a perfect example, but we don't know that it's aleph 1. And so, are there, for example, just the aleph 1 sized concepts that...
how about things like cardinal invariance?
Cardinal invariance of the continuum. Yeah.
Yeah. Yeah, we have a good example, but we have the definition of truth as schema. I have showed it in the beginning of my presentation. It is something like this. This is indeed directly a schema. V is the truth predicate satisfying this. We can add this schema to our theory. But indeed, this schema is recursive because it is for all phi. But which it of course does not answer what are the arithmetical truths, of course. So it is just the equivalence, the Tarski T schema. Yeah. So that would be also a mathematical notion that yeah, could be well. It is not exactly an undefinability issue, but more like a knowability issue, and the relations between those two things are a bit tricky, but it is not the same thing. But yeah, that's a very, I am very much interested in this, and in particular, we could strengthen our agreement. I think I have one good example for your question, which is a great question, and it is a question that I am thinking about indeed, to strengthen our agreements from our agreement is this. Syntactically, it is symbolically, it is the same. The symbolic layer is the same. The interpretative layer is omega models. A new agreement. Transitive omega models. It isn't strengthening, but what it is gained, just forcing, we have just forcing to tell us, but I don't know what is fixed here that is not fixed here, but definitionally. In terms of concepts, not in terms of facts, but in terms of concepts. If we change the interpretative basis from omega models to the transitive omega models, and this is reasonable step, right? This is a reasonable agreement. This is a reasonable agreement because set theories basically only work with transitive. It is. You can say, well, it is absurd to think that we have a set, but the set exists, but one of its elements does not exist. Wow. So that could be embedded in our basic semantic agreement without much arguing. What is the theory of definition for this? Do we have Beth? Important open problem.
There's no problem with reconstruction of layer paradigms.
So no, because you cannot. It is not a formula here to diagonalize. So you have this new predicate indeed, which is you can, without omega logic, add a new predicate to ZFC and conservatively extend it, saying that this new predicate is a truth predicate. So this is this extension of ZFC with a truth predicate. What is a truth predicate? One satisfying Tarski's truth schema, right? Is conservative. My point is that this is a bona fide extensional definition of ZFC. We should regard this as a definition. It is not an explicit definition by a single formula. It is a schematic definition. So I am talking about this. Forget about omega logic. You just take ZFC, add a new predicate symbol V, unary, and add all axioms of the form in which V does not occur in phi. This is a conservative extension of ZFC. No omega logic involved. Is this a definitional extension of ZFC? I think so. And I can give a framework in which this makes sense. Why is it? It is not an explicit definition, therefore not an implicit definition in first order logic. But it is an implicit definition in omega logic if we interpret this as a standard number. So that's the reason for the we require that the things entering V are standard objects. The things that go inside V are only allowed to be the standard ones. And so this is indeed an implicit definition in omega logic, but not in first order logic. In first order logic, V will have non-standard interpretations, which is not the truth predicate. No. Because you are not saying you are not saying what you are saying what happens to the standard phi's that go inside, but you are not saying nothing in these axioms about the non-standard things. Well, but yeah, there are no non-standard phi's, so that should be excluded in the semantics. The semantic agreement should exclude those. So there's no diagonalization there because
yeah, just also a curiosity. You are claiming that we have an agreement from a syntactical point of view. So you are proposing a neutral syntactical standpoint, right?
Yeah, I have not changed, at least I have not changed the symbolic agreement.
Yeah, yeah. But a good part of logicians claim that or believe that logic is primarily model-theoretic activity. So for those people, you are actually proposing a change of commitment.
Yeah.
And do you have an argument in favor of this change, or you just not worry about those kind of people?
No, I am worried about those kind of people. But for logicians, I am not proposing this. I am proposing this for mathematicians. So I am not identifying logical semantics with mathematical semantics. Mathematical semantics includes standard natural numbers. Logical semantics does not include that. So, logicians are not committed to number talking. In general, so philosophical logicians are not worried about numbers. They use logic, and they will use numbers in the syntax, of course, but they use logic not to talk about numbers or stuff like that. Mathematicians use logic to have knowledge about numbers and geometry. So yeah. Last thing I said, I would say, yeah, Esse outro. Yeah. Okay. For John.
Just in case it wasn't. You can hear now?
Yeah.
Okay, well, so I just asked Rodrigo what his last few words were. Where do they fit in this scheme of frameworks that I proposed?
This is a very good question, John, and I have dedicated some thought to it. I think it is about the discussion of what our ultimate meta-language is, the meta-language in which deep agreements are made. So, or maybe not the ultimate, but maybe the ultimate thing there is the framework that you have mentioned that cognitive scientists study. So it is the framework in which babies learn. What you have these two books. One of them you have mentioned in your cited. One of them is the origin of concepts, and the other one is what babies know. And both very serious research works on the acquisition of concepts of agreements, right, by babies, right? Maybe that framework, not of the cognitive scientist, but of the baby, is the ultimate meta theory. But I think here we are in the naive, which is your first framework, the naive framework in which we try to agree on the basic practices of mathematics. So, but of course, I don't know if it fits well with the framework hierarchy, because I assume that we are discussing the mathematical practices in some appropriate terms. So we must have some terms to say, well, mathematicians seem to agree in their practices on what they mean by standard natural numbers or natural numbers. Mathematicians talking about natural numbers, from the outside, it seems that they consider that there is an ambiguous thing, right? There is the natural numbers that they use in their inductive constructions, even if their theories are not directly about them, but somehow the natural numbers appear there as sequences of points or of degrees of mappings or in some other way. And so I assume that we are at this level of discussion. So mathematicians agree and disagree in their practices on this or on that concept. But
so I would have thought that, is it on now? Yeah. Was that we are certainly at least at level 3 because we're talking about formal languages, and it was really a question of logicians asking these questions or philosophers. It seems, or cognitive scientists. I mean.
Oh yeah. So in a sense, it was last framework. Yeah. Yeah, in a sense, not the first frame, but the last framework. We are on the standpoint of philosophers. I think of myself at the standpoint of a philosopher, trying to understand some real phenomenon that is mathematics. And I have given many features of this phenomenon, right? This is a convention, but not human, much too human. It is not arbitrary. It has some specific features, very specific features. So I think I am okay with the last level, but meta-theoretically, it is the less formal because all formal stuff will be based on this level of discussion. So all formal constructions that we adopt, okay, we are discussing which formal languages are good and they are there just, but the institution of formal mathematics depend on this level. So it is in a sense, in this sense, more basic than we must agree on what is the symbolic life, what is writing. So writing was developed, as I was told, to fix the sacred texts, because the oral tradition is too much fluid. It is lost. It changes very fast in distance and in time. Right? It really changes very fast, oscillates strongly. And then people were worried about preserving some tradition. So we started writing some things. And we must agree on what can count as well. If this is to fix, it must be for everyone. So it fixed the text, that is. There is an agreement involved that this fixing is for everyone. It is the same thing written. So we are in this level, and at this level, so this level is in a sense more basic than. But I agree with you. It is the philosopher framework.
Why does this agreement commitment doesn't change for logicians? Because like replacement axiom, and set theory, and logicians are working in set theory, so it's
but not all logicians are working in set theory. So if we look at the logic tradition, we get logicians are concerned with.
But we use sequence of variables. You gave the example of
but
sequence
Aristotle
of
don't use that.
Okay, but we're talking about logicians nowadays.
But you are talking about some logicians, I think. So logic was not mathematics for a long time. So and I think it is not. Still not mathematics, in that logic has some more neutrality. No? So for example, In this context of omega logic, all omega models are infinite. All omega models are. This does not change anything for mathematics, because if you think of mathematicians as working in ZFC, all ZFC models are infinite. So it is not this is not a radical change on the basic semantic agreement behind mathematics, because mathematicians have the axiom of infinity inside, interpretatively. But logicians are not like that. Logicians are not only concerned with infinite domains, for example. They are concerned with reason in general, so maybe not only with this infinite context reason. But yeah, maybe Russell, for example, is a logician that would be in that. He thinks that it is obviously there are infinitely many things. Oh. Yeah, but not all logicians are. Most of them are not. So. No, we can say that, but it is. We can say that it is part of mathematics, but that part does not necessarily includes the natural numbers. So. I'm thinking of mathematics as a whole is in this sense more in this sense more than first order logic. That is, all first order structures are embedded in omega structures, but not all omega structures can be embedded in first order structures. So the omega agreement eliminates some first order structures of consideration. So that is the some first order structures are not cannot embed an omega structure. A finite first order structure cannot embed an omega structure. So, okay.
Questions? Let's thank Rodrigo for the excellent Minicursos.
Okay, thank you.
Thank you, everybody. It's amazing week. And tomorrow we'll have a conference. It's 9:30, 9 more or less.